So let's talk about some of the unique features that NTFS adds. One thing is called named alternate data streams. And what this is that a file can have more than one stream of data. So multiple sources. Compression. This wasn't totally new with NTFS. There was a company called Stacker early in the 90s that actually created a disk compression system where behind the scenes it would go ahead and compress the entire disk, and it was totally transparent to the user. But of course, as the story goes about that, Microsoft stole the technology. Stacker sued Microsoft and prevailed. I think they got a $128 million settlement plus royalties on all DOS 5 shipments. But anyway, NTFS uses a LUNs compression algorithm. Now, I want to be specific. It's really LZ77 or a version of LZ77, or sometimes called LZSS. There's another one called LZ78 or LZW, and that's a totally different compression algorithm. Essentially, it's a sliding window compression algorithm, and the reason they picked it was because it's fast. They actually had to lean towards something that was fairly quick because it had to go on in the background and not slow down the disk access too much. It's chunky. It operates in 64K chunks. This is actually to optimize its performance. Like I said, there was a definite emphasis on performance. So it's only supported on cluster sizes that are less than or equal to 4K, which should be good since most NTFS volumes use 4K clusters. There's another idea called valid data length, and this helped with performance. It was a high watermark for where a file has been written. It allows for efficient creation of large files. This has to do with pre-zeroing the entire file, which would take a long time. Now let's go into features that were added in Windows 2000. Well, we've already talked about the journaling. So Windows 2000 added USN journaling, which here again is going to make the entire file system more robust, allow better recovery from errors, allow recovery from even, say, a power down. So a reparse point is actually a way that can store user-defined data. You can think of this maybe as a tag that was inserted. The quota system allows different users to have different quotas for resources on the disk. The secure file meta file is more metadata, as we've talked about before, and this allows a whole lot more security. Object IDs allows a better identification of different resource objects. File level encryption is an enhancement. Used to be that the only encryption you could have is a disk level encryption. Now you can encrypt just a single file. And sparse files. This is a way of dealing with large files that have very redundant data. And in most cases, the data contains a lot of zeros. So the USN journal, this is an efficient mechanism for applications to detect which files have been changed. And when we looked at the MFT, we talked about a lot of the mechanisms there that helped us out. It's also used by the background search indexer. Changes are tracked with a bit mask of reasons. And some of the more common reasons are file create, file delete, data overwrite, data extend, and renames. So the reasons can actually accumulate until a file is closed. So you might have a number of reasons. So the USN record also contains file name being changed, file ID of file being changed, file ID of the parent directory, USN number, and timestamp. All of these are going to be part of the USN journal. It's disabled by default but can be enabled per volume. Now that's just in Windows 2000. Reparse points. These are mechanisms for triggering special processing of a file or directory by a file system filter or the I/O system. They're processed at open time and can be triggered by any path name component. They consist of a unique 32-bit tag, and these are allocated by Microsoft, and they can include up to 16K of associated data. So as of today, there are only two supported uses, data redirection and file name redirection. So a special index which tracks all reparse points on a volume is $extend $reparse $$R. So we've already mentioned the quota. It supports per user quotas, supports soft and hard limits. It has been superseded with File Service Resource Manager. It itself is implemented as a file system filter. Okay, so that ends everything that was added in Windows 2000. Now let's talk about what was added in Vista. Many people think of Vista as the evil operating system. TXF, what is it? It adds basic database-like transaction semantics to file system operations. It provides ACID guarantees for transacted file system operations. This is really super important. We normally think of ACID as it applies to databases. But in this regard, file system operations also observe these ACID principles. Atomicity, all operations either commit or roll back together. Consistency, consistent state across multiple files can be maintained. Isolation, changes are not visible outside the transaction. And durability, on commit, changes are durably stored to storage media. So ACID supports file system operations such as create, close, write, delete, and rename. So what would be an example of TXF? Well, it would create a transaction, create file A, delete file B, rename C to D, and then it would commit the transaction. So all of those three operations would be part of the transaction. Applications outside the transaction would not see any of the above file system operations until the transaction commits. What are the TXF limitations? Well, a file can only be in one transaction at a time. And while that might not seem like a big limitation, I've encountered situations where it really is, because some files are used by multiple applications in multiple parts of the operating system. A file in a transaction cannot be modified outside of the transaction. File names used in transactions impact what file names can be used outside of a transaction. Functionality being deprecated in Windows 8 and beyond. So NTFS is also self-healing. It has always had the ability to detect metadata corruptions. Its response was always either to mark the volume as corrupt or fail the operation. With self-healing NTFS, it can not only detect corruptions, but it also can repair many of them. It only repairs certain MFT-related corruptions, and we've talked about a lot of those before. It repairs failure without failing operation. So Windows 7, in my opinion, has been one of the best operating systems that's been introduced. It introduced a per volume control of short file name generation. Okay, before Windows 7, short file name generation can only be disabled globally per system. So this FSCTL program that we've already seen last week, it could set or disable 8.1 operations. It required a reboot to take effect. Windows 7 added the ability to enable, disable short file name generation on a per volume basis. When disabled, it prevents short file name generation. Existing short file names, though, continue to function. It also added support for stripping short file names from a directory hierarchy. Here's an example: FSUTL 8.3 name strip. It improved the short file name hashing function too. Configuring short file name generation. So here's this FSUTL again, and you can use it to set the 8.3 functionality. Change takes effect immediately, no reboot required. And it has 4 global modes of operation. 0 is enabled on all volumes. 1 is disabled on all volumes. 2 is per volume configurable, which is the default. 3 is disabled on all volumes except the system volume. So what is the short file name generation performance impact? Short file name generation does have a performance impact. It has a small impact for directories with 30 to 40,000 files or less. Beyond this threshold, though, the performance impact continues to increase. What is ATA trim? The ability for a file system to tell the underlying storage system that the contents of sectors are no longer important. It is part of the T13 ATA specification. Why trim is important to SSDs? They need to maintain a pool of erased blocks. They need to wear level blocks. Wear leveling is more effective the more blocks that are available. Trim allows file systems to identify sectors that are no longer in use. That means that more space is available for internal block management. The trim implementation in NTFS goes as follows. When a volume is formatted, all clusters in the volume are trimmed. Anytime clusters are freed, they are trimmed. And this includes file deletion, file defrag, create, rename, and volume shrink. It is not supported on SCSI or SAS devices. So here's an example of how trim works. An application calls delete file. File system metadata is updated and written to the device. Metadata is flushed and checkpoint record written to log. Now the device is notified that blocks are no longer in use via trim. Blocks are now made available for reuse. You can disable trim. Trim is always sent by NTFS. To disable it from sending trims, FSUTL behavior set disable delete notify with a 1. This takes effect immediately. No reboot is required. This is useful in situations where data recovery is more important than SSD efficiency. For example, offline undelete tools or unformat tools. What are enhanced oplocks? Okay, before Windows 7 there were 4 types of oplocks. Level 2 supports caching of reads. Level 1 supports caching of reads and writes. Batch supports caching of reads, writes, and handles. And Filter supports caching of reads and writes. But it has the additional semantics that allow its holder to unobtrusively access a stream. But there were some problems with oplocks. The cache levels were insufficiently granular. It was too easy for an app to break its own oplock. For instance, Office applications did this regularly. Batch and filter oplocks may be broken in a create that will ultimately fail anyway with the status sharing violation flag. Atomically, request an oplock at create time. This meant that it was impossible to implement an unobtrusive background scanning application. There were some Oplock enhancements. These enhancements can specify caching with a combination of flags, such as read, read handle, read write handle. Additionally, oplocks can be associated with an oplock key, and this means that operations on handles with the same oplock key won't break the oplock. They can also perform a sharing violation check before breaking oplock. So this means for atomic creates, you can use oplock semantics. Now let's move to Windows 8. So there was a very important thing that was added to Windows 8 called offload data transfers, normally referred to as ODX. So here's the way data moves today. It comes out of memory or possibly virtual disk into the PC, goes across the wire to another PC, which then stores it either in RAM or virtual disk. So reads and writes are very well understood. And this works well with the OS security model. Security checks occur at open time. It also works well with the application programming model. There are some inefficiencies with today's model, such as data flowing out and back into the same storage system. Also, another inefficiency is data movement consumes CPU and memory. The last thing is the data movement may consume network bandwidth. So ODX is here to the rescue. It takes advantage of advanced capabilities present in many of today's storage units to enable efficient data movement. Rather than pass the data around, it passes around a token which represents a point-in-time view of the data. It supports cross-machine and cross-subsystem data movement while not constrained by protocol transport or geo-boundaries. Maintains well-understood security framework. It offers an easy and familiar programming model for developers. It enables applications to participate in efficient data movement. So let's talk about reading the data. ODX instructs storage to generate and return a token which represents an immutable point-in-time view of the requested data. The token is completely managed by storage. It's opaque to the OS. Then ODX functionally equivalent to a normal read operation. The operation behaves like a non-cached read. One caveat though, it must be sector aligned. This performs standard oplock and byte range lock processing. Now let's move to writing the data. Given a token, the storage attempts to independently execute data movement to the desired destination. It attempts to recognize the token. It determines where the data represented by the token is located, determines if the data movement is possible, performs the data movement, and all of this happens without OS intervention. This is functionally equivalent to a normal write operation. The operation behaves like a non-cached write. It performs standard oplock and byte range lock processing. It also updates the USN journal, which turns out to be very important. The limitation, though, it does not allocate disk space. The space must be pre-allocated. We saw an illustration of how, in the past, data has moved. Now we're going to see an image. Now we're going to see an illustration of how ODX data movement works. So the old model was from virtual disk to the PC, across to the other PC, and then back to virtual disk. Here, the actual data transfer happens independently of the OS. So here's the support in Windows 8. It enables offloaded transfers. They are supported to the same volume on the same machine. They're supported across different volumes on the same machine. They're supported across different volumes on different machines via SMB, and they're supported by Hyper-V. They're integrated into the Win32 copy file API, which has been around for quite a while and is used extensively. Any component that uses this API will automatically use ODX when available. So this is without any kind of intervention by the developer. ODX will step in and manage it. If ODX is not supported, normal read-write copy semantics are used. It is supported by copy, xcopy, robocopy, as well as explorer drag and drop. So now the bad news. There are some limitations. It's only supported by NTFS. It's not supported on compressed files. It's not supported on encrypted files. It's not supported on sparse files. It's not supported by BitLocker. It's not supported on snapshot volumes. And it's only supported by SANs, which implement xcopy Lite. Windows 8 also had a check disk overhaul. I'm not sure if you've ever used that, but it's a pretty useful utility for a lot of things, which we'll actually explore a little more in depth in this course. NTFS volume scalability. NTFS now supports volumes up to 256 terabytes in size, which is very, very huge in my opinion. Of course, if you're the NSA and you've got the Utah facility, it's not. But for mortals like us, it is. The practical volume size is smaller based on check disk execution time. Check disk scales based on the number of files in the volume, not the size of the volume. Check disk execution time has improved with every Windows release since Windows 2000. But there is a limit to what additional improvements could be made with the current execution model. There's a new approach for detecting and repairing corruptions in NTFS. The enhanced detection and handling of corruptions in NTFS happens via online repair. It changes the check disk execution model. It has two separate analysis and repair phases. The file system health is monitored via Action Center and Server Manager. It also supports enhanced NTFS corruption handling. NTFS now logs information on the nature of a detected corruption. It is maintained in new metadata files. These include verify and corrupt. This provides enhanced event logging, which includes more detailed information. It also provides new verification component, which confirms the validity of a detected corruption. So in many ways, this eliminates even the need for check disk runs, but I still like it because I feel comfortable with it. So it extends the self-healing features that were introduced in Vista. It is limited to MFT-related corruptions, though. It is also enhanced to handle a broader range of corruptions across multiple metadata files. It can do online repair of most common corruption scenarios. So what is the new model for check disk? Well, the analysis phase is performed online on a volume snapshot which maintains volume availability. Okay, I'm not sure if you remember, but before, check disk used to have to actually reboot if you wanted to check your system volume, and then right at reboot time it would run check disk for you. If a corruption is detected, first it attempts an online repair via the self-healing API. Next, if self-healing cannot do the repair, the detected corruption is logged to a new NTFS metadata file, $corrupt. All logged corruptions are verifiable. An online repair phase, if needed. A volume can be taken offline at administrator's discretion. Only repairs logged corruptions to minimize volume unavailability. This normally takes only seconds. And if you ever remember using check disk before, It would sometimes take 30 to 40 minutes, which was a really long time. So Windows 8 also brought a maximized file system availability model. Here's an illustrative example.